start on the 2nd. We have some loss, I see, of people. It's a pleasure for me to welcome Olivier Bousquet. He is French, and he studied at all these big écoles in Paris. In 2002, he got his PhD from the École Polytechnique on concentration inequalities and empirical process theory for machine learning. His thesis was awarded the best thesis of the École Polytechnique, and he also earned the best paper award at the conference on learning theory during his PhD time. After his PhD, he moved shortly to the US, and then came to the MPI here, where he worked for 3 years as a senior postdoc. And that was before he turned to the dark side and went to industry. Back to France, in Paris, he worked at Pertinence as a research manager and recently moved to Google in Zurich. In his research career, he was mostly interested in learning theory, but he also contributed to more applied things. So I heard you are co-author on semi-supervised learning paper of Denny. So he also knows what theory is good for. Before I give the word to Olivier, just let me mention that he was also the organizer of the last machine learning summer school in Tübingen. So I guess it's nice for him to speak here again. Okay.
Good morning, everyone. Thank you very much for this introduction, and I wish to thank the organizer for inviting me, first of all. And also, as Florian said, it's kind of an important moment for me because 4 years ago I was in this room and I was introducing the other speakers. And I know it's a lot of work, and it's very difficult to organize such an event and to make it successful. And this one seems very successful so far. So I won't be here at the end, but I hope you will all give them a lot of applause at the end to congratulate the organizer for this nice event. Okay, so I know it was a bit, it was a very nice dinner yesterday and a lot of drinks, so probably you will not be completely awake for the entire duration of this talk. So I will try to give you a very slow start this morning. And as Florian said, I have turned to the dark side, which means that I started thinking about, what is this all for, this theory? How does it help in practice? And does it really make a difference in the real world? I mean, when you're in a company and someone asks you to design a learning algorithm, does it really help to have proven theorem before? And so what I will try to attempt in this lecture is to show you that all the details, the mathematical details, you can figure them out, right? You look at the papers. Once you know enough of what are the definitions and all that, you can more or less figure out the details and understand the proofs of the papers. What is harder though is to understand the meaning behind those proofs, or really what you can infer from these theorems and what you can do in practice, and how does it help you or guide you towards building the right algorithm. And so this will be really the goal of these lectures. There will be 3 parts. So today we will look into what I call the what and why, which is what is learning theory and why are we studying it, and what are the foundations. And we'll in the second part of this lecture we'll discuss about the no free lunch theorem, which is I think an important piece of it. And tomorrow we'll go into the bounds and I will show you how to prove some bounds and how to play around with the different techniques that exist. And day after tomorrow I will discuss about the implication and the consequence and how to interpret these things. So again, the goal of this course is not really to give you a lot of the results and a lot of proof, but more talk about the foundations, keep things simple, and really give insights. That's what I'll try to do most of the day. Most of the lecture. And I will, of course, not cover things like the history of the domain or general results and advanced topics. So let's start. So before telling you what is learning theory, I have to tell you what is a theory and what is the goal of, defining a theory about learning. So this is, definition of what is a theory, and I have emphasized the important words here. Important is that we are looking at a phenomenon and we try to explain this phenomenon, and we want to explain it in a repeatable way, and also this explanation should help us make prediction about this phenomenon. That's the important point. So in a way, you can think of a theory as a model, something that kind of represents or describe some phenomenon, and that model helps us understand the various things that happen when you observe this phenomenon. In this case, it will be the phenomenon of learning, of course, and of course predict what's going to happen later. Two more definitions that will be useful during this lecture. Deduction and induction, these are often opposed, and actually they are opposed if you look at the definitions. So deduction is really, you go from the general axioms, the general rules, and you try to derive consequences. So you go from the general to the specific, and the specific is, say, a theorem. So you go from the axiom and you derive your theorem, you prove your theorem. So this is really what mathematics is all about. Induction is more what physics is all about, which is you look at a specific examples, you make observation about nature, and then you try to infer the general principles, the axioms of nature, if you want. This is how you create theories, usually, from observing nature. I mean, there is also something in between, which is called transduction, which you probably have heard of, which is going from specific to specific without even mentioning a model. But these are two important things, from general to specific or from specific to general. So what is a good theory? A good theory is one that is, intuitively makes sense, of course, and which is simple and concise. So you have a lot of observation. You can look outside and observe a lot of natural phenomena. And if you can explain all these phenomena with a very small set of axioms or principles, then you are happy in a way. So you want to explain many things with few things. And these principles or these axioms or postulates, they can be called assumptions, axioms, postulates, or any. There are various denominations. An example of them is the following one. So the principle of relativity, the laws of physics are the same in all inertial frames of reference. So this is really something that you can't really prove. You just say, okay, let's assume this is true. And if this is true, what can we derive from that? And what are the consequences? So that's the important point here. The assumptions, you can never prove them. You can only, kind of figure out what are the consequences of these assumptions, and then go in the nature and try these things and test whether they're true or not. Test the consequences. And of course, a good theory should have few of them. So we have defined what is theory. Now let's define what is learning. So learning, you all have pretty good intuition of what is learning, but let's make things precise. Learning definition you can find in dictionary is to gain knowledge, comprehension of, mastery of through experience or study. Study is kind of the easy case. You study something, you know it. So we will not focus on this part of it, but more on learning through experience. So you do something, and as you do it, you kind of gain knowledge, comprehension, like understanding. So in a way, you build your own mental model. Right. So interestingly, the interesting part is when you don't just accumulate observations, but you really create your own representation of the world, and you have some internal model that allows you not only to account for what you have observed, but also allows you to make predictions about the future. So, all these words, you can consider them as meaning the same thing in the context of this lecture. So this leads us to an interesting I mean, if we look at the definition of learning and definition of a theory, we get some kind of weird circularity here. So we have said what is a theory and how it should be constructed. And theory is really making observation and constructing a model of these observations. And the question is, why did I tell you all that, right? Actually, building a theory is really the same as induction, which is the same, as I said before, as learning, right? Learning is you observe things, learning from experience at least, you observe things and you make a kind of internal model of these things, and building a theory is the same. So, you know, it's kind of circular here. I'm telling you that learning is building theories, and I want to build a theory on building theories. So let me rephrase that a bit. So induction is the process of building theories. Learning theory, the main focus of learning theory is the phenomenon of induction. So how can we build a theory about building theories? Okay, so I mean, I won't go more into the details of that, but it's just to emphasize that this whole thing is involving a lot of philosophical issues, and I will touch upon some of them later on. But let's try to go a bit further now. So, okay, now you have a rough idea of what is it that we are trying to do with learning theory. Now, why is it that we are trying to do that? I like this quote. I mean, you can find it in Vapnik's book, and I think it doesn't say that it's from Kurt Lewin. Well, I mean, I don't know. I looked on the internet, and that's the kind of reference that is given most often. But maybe it was reused by so many people. So, I mean, yeah. What else can I say? No, I mean, more seriously, these are the things that I think are important. First of all, we want to understand what's going on when we do learning, right? And we want to study the properties of different learning algorithms and be able to say, okay, this is better, why, and in this context, this is better, and this other algorithm is better, and not just by trying it on various kinds of data, but by being able to say, I mean, to make some general statements. And ideally, that should lead us to, a way to design better algorithm for certain tasks. So again, this induction versus deduction, I mean, I'm kind of repeating the same thing over and over again in various flavors, hoping that you will get the main message here. So if you compare induction and deduction, that's really what is kind of most frustrating about studying induction, is that deduction can be easily justified. I mean, once you have agreed upon the axioms, then you kind of derive, and the rules for combining these axioms, then you derive the consequences, you prove your theorem, and nobody can disagree. I mean, this theorem is correct, provided that everyone agrees on the axioms. For induction is exactly the opposite. You can't really justify anything. Someone comes up with one axiom about some observation. You can only test the consequences of these axioms, so make deduction from that and then check that it's true. I mean, check that it corresponds to or correlates to your observation. But you can't really, prove or disprove an axiom, and you can't really argue about the truth of some induction in a way. So let's see. I mean, let's make this now a bit more concrete, and I will give you some example to, force you to reason about these things. Here is an example. So let's say we observe the sun every morning, and we see that it's rising every morning. I mean, the usual example is whether the sun is rising from the east or from the west. But let's just say we observe that the sun is rising every morning for a number of d days. Okay, and the question I'm asking you is, okay, given that you observe that for d days, what is your estimate of the probability that the sun will rise again tomorrow? I have not defined what is probability yet. You have already, I'm sure you have already used that and you already know what it is, but I will go into the details later. But let's say you have some intuitive notion of what is a probability, and let's say I'm asking you what is your best estimate at this probability given this observation. There are many ways in which you can answer this question. The first one, you can say, well, P cannot be defined, right? Tomorrow is not identical to yesterday. It's just another day. It's not a repetition of the same experiments, right? You can't really compare 2 different days. So I don't want to define this probability because this is just a single event that cannot be compared to any other event. Okay, that's kind of the pessimist answer. The optimist answer would be the opposite. Say, oh, well, it's always rose so far, so tomorrow I'm sure it will rise. So P equals 1. Then you have the Bayesian answer, which is, well, let's assume that P, this probability P, I put a prior on this probability, a uniform prior on this probability between 0 and 1, and then I work out the details, I apply Bayes' rule, and I get this value here, d plus 1 or over d plus 2. Okay, so as d increases, this probability will converge to 1, but in the beginning, it's kind of more towards a half. And then there is the physicist answer, which is, you can work out the details. So the sun is a star. We know how many stars explode per day. And we can compare the sun to other stars with the same property, take into account the age of the sun, and so on. And we can work out the probability that the sun will explode tomorrow and not rise again. Okay, what do we gain from this example? Basically, all these results just converge towards saying that there is a high probability of the sun rising again tomorrow, and they all have different justification. And these different justification, really the point is that they differ in how they consider similar situation. Like in this case, it's like every day is the same. Here, you have some kind of probabilistic notion of a day plus, it's prior on the probability P. And here, the similarity is not over days, but over the kind of elements that we're considering, the sun and the stars. So it's really up to how you kind of relate the current situation or the future situation to what you have observed in the past. Okay, let me give you another example. Okay, so let's assume we observe this sequence of numbers, 1, 2, 4, 7. And the question is, what comes next? Any idea? Okay, that's one answer. But actually, there is not just one answer. There are, so far, and it keeps growing. There are 599 in this encyclopedia of integer sequences. So you go in the internet, you type 1, 2, 4, 7, and it gives you all the sequences that are known and start with 1, 2, 4, 7. And all are very good justification. So 11 could be 1, but let's see, what are the other ones? So 11 would correspond to this one, or at least could correspond to this one, which is the maximum number of pieces formed when you slice a pancake with n cuts. You keep cutting your pancake, and every cut you add n pieces. So you have 1, 2, 4, 7, 11, 16, and so on. And this sequence is called A124. Okay? But you could just think in another way and say, oh, this is just this recursion here. I take the previous two numbers, I add them, I add 1, and I get 1, 2, 4, 7. And then I continue like 12 and 20. This is perfectly fine, right? It fits with what we have observed. It's a natural, it's a relatively reasonable equation here, and we can carry on. Another one is what are called the Fibonacci numbers. Okay, yet another pretty simple recursion. And you can have some kind of different approach. If you're a bit original, you can say, well, let's look at the binary expansion of this sequence. So 1 is this, 2 is 10 in binary, 4 is 100, and 7 is 111. And if you count number of ones you have, you have an odd number of ones in all these numbers. So you can say, well, let's carry on. Let's keep looking at bigger and bigger binary numbers and just keep the ones that have an odd number of ones. And this gives you 1, 2, 4, 7, 8, 11, 13, and so on. Okay, so that's just as simple, right? Or, well, you can be even more tortured in a way and look at pi and e interleaved. So here is, I removed the 3, right? So 3, 1, 4, 1, 5, 9, that would be pi, and 2, 7, 1, 8, that would be e. And I say, well, okay, 1, 2, 4, 7, so the next one is 1. Why not? And, well, you can say, well, I'm observing 1, 2, 4, 7, but I think later on it will keep at 7. And this is my explanation for it. Okay? So basically you see that you can come up with as many possible expansion of that sequence as you wish. And it's, a matter of which one do you consider the simplest. There is no notion of simplest thing like in absolute, because some people would argue that the binary expansion is natural, like computers would argue that. Reasonable people might argue that this one is simpler. I don't know. I mean, it's really up to you. Well, some other example in the same vein. If you look at this sequence, you think, well, okay, with so many numbers, there is only one way to continue this sequence, right? You can be sure that, I mean, these are all primes, so the next one is a prime. Well, again, if you look into this encyclopedia, you can see two answers. One is the next prime, and one is another, which is the order of the next simple group. Okay? So you probably don't know what is a simple group, or maybe you know. But it doesn't matter. My point is, it's a matter of what you're most familiar with. And, people are more familiar with primes, so maybe we can say, okay, a natural continuation of the sequence is 61. But again, we cannot prove it, right? We cannot say for sure this sequence will continue with 61, and there is no other way. Another example which gives a little twist on that is the following. So we observe this sequence of numbers. Maybe it's familiar to you. But it looks random, no? I mean, it's just a bunch of numbers. Yeah. But, if you don't know this specific number that is very popular, like if I had given you another less popular number, you would have thought, okay, that seems to not have any pattern. So, and if you look actually at the frequencies, right, if you kind of count how many times each individual number occurs, and you kind of assume that the probability of the next digit being I is proportional to how many times you have observed this I divided by the number of digits you observed, then this probability, you can see that it will converge to 1/10. So you can say, well, this is kind of random in the sense that every number can occur with the same probability. But as you said, and have you noticed, I mean, this really looks like the expansion of pi, right? So, okay. So, why do we prefer this answer, the last answer? Well, because we obviously notice that there is a structure. Even though it's not, you can formalize it by some kind of recursion, like you cannot say un is equal to un minus 1 plus something. But still, we manage to notice that this is something that contains structure, and actually there is an algorithm that would produce this sequence and continue it. So this algorithm, you can think of it as a model for that sequence. It corresponds to this observation, and it gives you an expansion. So, okay, now let's wrap up. Is there a general principle for providing a good answer to these riddles, right? These questions of continuing sequences? Well, unfortunately, I mean, there is one approach that seems to be satisfactory, which is called this Occam's razor. You try to find an explanation which is consistent with what you observe and which is the simplest possible. But the problem is you can't really define this simplicity. So first of all, you cannot really justify that this will give you the best answer. As I said before, you can't justify these postulates, right? There is no proof that the simplest answer is the correct one. And second of all, you can't define simplicity because it's not objective. There are many ways in which you could measure it, and everyone would have a different notion. I mean, some people tend to say that the right notion of simplicity is what is called Kolmogorov complexity, which is a measure of the length of the shortest program that can generate some sequence or that can implement some function. But even that is not completely objective, because when you define the length of a shortest program, you first have to define in which programming language you write your program. And which means that every programming language would give rise to a different notion of length. So even though you can prove that asymptotically they are all equivalent, at least if the language is complete, Turing complete, in practice on finite sequences, each programming language would give you a different notion of simplicity. So if you observe a finite sequence, as we did before, there is, again, no reason to choose one or another. So it seems that we are doomed, right? I'm just saying, I keep saying, okay, we can't do anything, right? So what's the point? Well, let's see. Maybe we can do something, but it means we first have to kind of lower our expectations. We won't prove that something is the right thing to do, or, I mean, we won't prove that there is an optimal way of doing induction, but we can at least try to get some more understanding. So let me now define probability and discuss a bit about what probability means, because you've heard a lot probably before in previous lectures about probabilities. Maybe you also used that a lot, but I want to kind of make you think again about what is probability and what it means. So probability, I mean, to me, is just a way to formalize reasoning under uncertainty. So it's a convenient way to assign numbers to events, right? And it relies on these simple axioms that probability of an event is non-negative, probability of the certain event is 1, and then you have this additivity, like disjoint events have probability that sum up, and if there is some intersection, you can just subtract it. And, well, optionally, you can introduce this kind of sigma additivity of the probability, but it's not really relevant to understand what it means. Okay, so that's pretty simple, pretty convenient. You can make easy computation with these things. But the question is, what does it all mean? And more precisely, how you can measure these numbers, or how can you decide of which is the right number for an event. So there are a number of ways to interpret these numbers, and interpretation here means assigning a meaning to a given number. One of the simplest one is the so-called frequentist interpretation. So in the frequentist interpretation, probabilities are relative frequencies. So, how many times a certain event occurs divided by how many times you tried this. And I will get into details. Objectivism is more or less the same. I mean, you can say the probability is still a frequency, but now this frequency is not observed as in frequentism, but it's kind of postulated as something that exists. And you have the subjectivist point of view, which says that, well, probabilities are just beliefs. It's just something that we think is true, but there is no way to prove that it's true. So, okay. So probabilities as frequencies. So what you do is, as I said, and as is natural, you repeat a given experiment n times, and if the event of interest occurs k times, then k over n is your estimate of the probability, and you can even define the probability of this event as the limit, right? So you can say, well, if I were to repeat this experiment an infinite number of times, eventually this limit might convert to some number, and this is how I define probability. Okay, that's kind of clear and easy, but the problem is you can't always repeat experiments, and also you rarely can repeat infinitely the experiments. So you cannot really have a measure of these numbers by experimenting, because you can't really reach that limit. And probability of sun rising tomorrow, how can I repeat? So there are some limitations. So the objectivist interpretation, it's kind of, it's kind of a leap of faith. You say, well, I can measure, I can try to measure these probabilities, but I'm assuming that they exist, and this is some kind of intrinsic property of the word, that there is, like, the sun has attached to him, or attached to it, some probability of rising tomorrow, and this is kind of a property of of nature, and I can only observe it. It's like the mass, right? The sun has some mass, but it also has some probability of rising, and I just want to measure that. So these probabilities pre-exist. And the last interpretation, so for the subjectivist interpretation, these probabilities, they are just numbers that people, a given person would assign to some events, and that correspond to how how strong his belief is that this event will occur. And there is you can naturally define, naturally assign these beliefs, assign numbers to these beliefs, real numbers to these beliefs. And then, you can come up with the natural or intuitively natural rules for combining these beliefs when you believe in one event, and you have a belief for one event and for another event, how you combine these beliefs and so on. And you can show that if you use these natural rules, then it will lead you to something that has the same properties as probabilities. So essentially, probabilities are the right way to formalize the natural notion of belief in something. And then once you have kind of chosen one of these interpretations, you don't have to choose it, basically. You can just run your calculations without even thinking about how to interpret these numbers. And one way in which you can combine these numbers besides the axiom, you can derive that from the axioms, is what is called the Bayes rule. And what it is just a way to update your probabilities when you make observation. So you have prior beliefs in some hypothesis, P of H. You have some way to measure how, what is called the conditional probability of observing some data given the hypothesis. That's again some belief that you define, or some number. And the natural way to derive from that how much you believe in your hypothesis after you have seen the data is to apply this rule. And this is kind of, if you want to be consistent with your axioms, that's the only way you should do it. But again, you can't really measure all these numbers, but once you have agreed that this is the right things to do, you can just work out the details. So again, my point here is, what can we gain using probabilities? Is this the right way of doing inference or doing induction? Well, it's a natural way to do it, or it's a convenient way to do it. You get these nice formulas, and you get these nice numbers that you can combine. But we don't gain anything, right? We still cannot prove that what we are saying is true, because we don't get any guarantee. The probabilities, they just help us reasoning, but if we did not set these numbers right in the first place, But even if we set them right, I mean, because there are so many ways to interpret them, you can't really prove that the probability of something is some number, because you can come up with all sorts of interpretations. You can be a frequentist or an objectivist or a subjectivist, and none of these people would agree, right? So again, it's kind of disappointing, but even though you are using probabilities, it doesn't mean that you're doing the right thing or that you're justifying anything. So in a way, the problem is that we need these assumptions, and there is no way we can escape these assumptions. And so what can we do? What we can do is, implicitly assume something like the future looks like the past. This is kind of reasonable, and everyone would agree with that to some degree. Or what we have not seen yet looks like what we have seen. And it's clear that if we don't make such assumptions, then there is no point in doing any, in working in learning theory or even working in machine learning at all. Because if you don't assume that there is some regularity in the world, there is no hope that you can uncover it with these algorithms. But still, we want to make these assumptions, as limited as possible. We don't want to assume too much, and we want to keep them to a minimum, which means that maybe we can even completely get rid of this assumption. And actually, you can, in a certain sense, if you don't aim at proving that some algorithm is optimal, but if you want to compare algorithms, like if you don't want to predict, but to predict well, but you want to predict as well as some other algorithms. So if you want to imitate the behavior of an algorithm, independent of how good that algorithm is, then you can, somehow get rid of these assumptions. So it's a matter of, can we match some other's performance? And when we are willing to go with assumptions, then the question is, and the question that the theory should answer is, given these assumptions, what can we do at best, right? So what is the optimal algorithm with respect to these assumptions? That's something we can answer. Okay. Now I want to kind of slowly go towards more formal things. I hope it's not too slow for you. I fixed myself a quota of 5% of people that should be asleep by the end of the lecture. So far, it seems to be okay. Maybe 3% yet. Okay, so maybe I need to be a bit faster. So let me introduce now. I'll try to describe a picture of the things. Let's say, how to distinguish between different assumptions or frameworks, because you probably have heard about, online learning or semi-supervised learning or Bayesian inference, and all these things. I want to kind of draw a chart where you can place these things and relate them to each other and understand what is an assumption and what is just a matter of setting the problem and so on, and trying not to confuse all these things. So here are some examples of settings that are commonly used. So the so-called offline supervised learning, you have training pairs that are given to you, and the goal is to produce a model that predicts well on future instances. Semi-supervised learning, you have both training pairs like X, Y, and also unlabeled data, and you want to produce a model that predicts well. So you want to produce a function that assigns a label to every future instance. Transductive is slightly different. You have the same inputs, training pairs and unlabeled data, but the goal is to predict well on unlabeled example. So the new X, and you want to predict the Y, and so you have to predict the performance at each step whenever you get a new example. And there are some variants that you probably have heard of, like reinforcement learning, where instead of predicting some label, you want to take some action, and then you get some reward, possibly not immediately, but later on. So these are what I call settings. That's the way you set up the problem and what you ask your algorithm to do. Now, you should not confuse these settings with the assumptions that you put on top of that. Usually the assumptions are about how the data is generated in these cases. Like if I go back, how do I assume that these data is generated, these training pairs or these instances that come one at a time. So, you probably, a natural way is to say, okay, they are generated by some probabilistic mechanism, some random number generator or something like this. Or maybe they are generated by some natural phenomenon, observing nature and so on. And these assumptions, as I said before, they are only used if you want to prove anything, but otherwise, they don't really make sense, and you can't really justify any of those. So, who cares? The protocol is more, how you set the stage of your learning problem, and how the instances are coming to you, and what you get to see of these instances, and so on. And this is really the relevant part when you want to create algorithm, because your algorithm have to fit with this protocol. Then there is this notion of success measure, which is how you would be measuring success, or when would you say I'm satisfied with this algorithm. And sometimes the success measures are abstract, like, for example, the reward in infinite horizon, like how much you will, or the number of errors you will make if you add infinitely many data points, this kind of thing. So these are target criteria, but you can't really measure them. You never will have infinitely many data points. But they help you, or they guide you towards deriving the right algorithm. Then there is what type of analysis you are doing in this, given this setting, given this success measure, given your algorithm, how you will analyze it, and what kind of statements you are expecting to prove about this algorithm. And again, that's relevant. That's only relevant within a certain data generation mechanism. And sometimes you also have further restrictive assumption. So you kind of assume some regularity about the data, or you may assume that you're only looking at certain kinds of functions, these kind of things. And this again is not really. It's useful for designing algorithm, because then you can restrict your algorithm, but then your algorithm would only work, or would only probably work under these conditions. The point here is that if you have an algorithm that has been designed under a certain set of, for a certain protocol with certain limiting assumption, this algorithm may perform well under some other circumstances. So my point here is that, people would tell you, okay, the algorithms that are based on Bayesian inference, for example, are working better. Okay, maybe. But, the thing is that you can prove that within this restrictive framework and within the right assumptions, these can be proved to be optimal, fine. But then beyond that, you don't know. You cannot prove anything, but still they can work well. So you can't really use the fact that an algorithm is proven to be optimal in a certain context to derive the fact that it will be good in another context, but it may just be good, just because it is good. Because it happens to fit with this, the assumption of this other context. And another point is that algorithms often have a proxy that they are trying to optimize, which is not the real success measure, but some measure that hopefully will converge to the success measure, for example. Okay, some examples of all these things. Data generation mechanism. You can have several ways in which you assume the data comes to you. In the kind of Bayes interpretation, you can assume that the underlying function describing your phenomenon is sampled from some distribution, and that the data also is sampled from some other distribution. So you put, probabilistic assumption or probabilistic generation assumption on both the function and the data. In the IID setting, IID stands for independent identically distributed. You don't assume that the function is sampled kind of randomly, but you assume that the data is sampled IID, so independently and
with the same distribution from some unknown distribution P. In the transaction framework, you assume that the data is completely fixed, but what is random is how you split this data into labeled and unlabeled, for example. And then, well, you can just read that. So the point is, these data generation assumptions tell you how you assume that the data comes to you, right? Now the protocols, I mean, mainly it's whether the data comes all at a time, like you get all the examples once for all. That's the offline case, or online you get one example at a time. And along with how the example come, you have some other things that define the protocol, which is how you define the error of your algorithm, or whether you whether you are available to you the error or the value of the error. No, sorry, the error function or the value of the error, or the error of other related algorithms. I mean, this will be clear probably when you see Nicolo's lecture on online learning. And I won't get into the details here, but just to give you an idea. Success measures, I mean, there are various ways also to define the success. Like one classical one is the expected error in the offline setting, where you take the average error under this unknown distribution. The cumulative error is like the sum of the errors that you make at every step in the online learning case. And you can have a combination of both if you have an underlying probabilistic assumption. So if you assume that the example come one at a time and they are sampled from some distribution, you can compute the expected value of this error. Now the type of analysis, this is what you kind of aim for, or how you want to define what is a good algorithm or a bad algorithm. And you can study the worst case performance or the average case. So worst case being like you consider the worst possible data generation mechanism within the ones that you have chosen, or average case is like you define some kind of probability on the data generation mechanism and you take the average over them. So it requires some weighting, like choosing what is the probability of each data generation or probability distribution. Or this case, which is like you are interested in the case that you observe. Okay, and then you can prove several different things given, for each type of analysis. So one example that we can detail a bit more is this Bayesian inference, and I'm using that in a kind of very general way, and I mean many people would have different definitions or would only consider the protocol but not the data generation mechanism and so on. So I'm trying to go through all these things that I've defined and tell you what would be the way people would do it in a Bayesian framework. So as I said before, in the data generation mechanism for Bayesian inference is usually that you assume that your function is sampled from some prior, and the data is sampled IID from this distribution, right? So, or from a prior distribution and labeled by this function. Depends on whether you consider function or distribution here. The protocol is often, you have offline, you see all the example at once, and the loss measure is the expected error under this data generation mechanism. And the type of analysis is, again, you average things under the prior. So it's kind of an average case analysis. And usually you also have restrictive assumptions, like you assume that the noise is of a specific form, like in a regression, Bayesian regression, you would assume that the noise is Gaussian or this kind of thing. Well, I mean, usually you assume that each instance is sampled independently from some distribution. So, I mean, there are two ways, right? Yeah, well, yeah, maybe it's not very clear. So, yeah, usually you have a different prior from the data for sampling the data. But there are two ways. So either you consider a function, you sample your data, and then you label this data with the function, or you consider a distribution here, so a distribution on x, y, and then the data is just sampled from x, y, so it's not labeled by the function. Sure. Yeah, I mean, okay. Yeah, maybe this is a special case. IID is a special case. That's true, because like some people would just say, okay, I get this data and it's sampled by from some distribution, which needs not be IID. And yeah, sure. All these assumptions you only need if you want to prove things, right? But otherwise you can. Well, also if you want to apply Bayes rules, right? You have to choose whether you want to write the probability of the observation as a product of probabilities of individual observations, which correspond to the ID, or you define this otherwise. Yeah. Okay, so in our case, we will consider more of a worst-case analysis, and we try to avoid assumptions as much as we can, and look for algorithms that do best under these few assumptions. And the kind of quantity that kind of is interesting to us is the following. We're looking at the loss of a given algorithm for some problem, and we look at the worst case value of this loss for the worst problem in a certain class, maybe. And hopefully we try to find the algorithm that is best with respect to this worst case loss. So the thing is, we will show that this value, which is kind of the optimal loss that we can expect under this worst case scenario, we will show that this actually does not need always to be small. So sometimes there is no way to escape, and that's the no-frillian theorem. Sometimes you cannot hope to make this small, so you can't really have a good algorithm. And there are several ways in which you can make this non-small, and I will show you how. There is a distinction to understand, which is a bit subtle here, is that you can put restrictions on the problem class. And what does this mean? So that's the classical minimax approach. What you consider is just what I wrote before, but you consider that the problem is within a certain class. So, for example, problem means the probability distribution, for example. So you assume that the probability distribution has certain regularities, say. And you can either consider the loss or the loss with respect to the best algorithm for that problem. The two cases occur. The problem is, like, if you get a statement, so if you prove that this quantity or this quantity has some value or is within certain range, the only thing you can say is that if my problem, so sorry, I should have said problem in a class here, so you have also this restriction on the problem. So the only thing you can derive from that is that if your problem is indeed within that class, so if your probability distribution indeed has these regularities, then you can say something about the loss of your algorithm. Or of the best algorithm. But if it doesn't satisfy these conditions, then you cannot say anything, right? So this is important. You have to understand that whatever restriction you put here would restrict the applicability of your results. Yeah, well, I mean, yeah, I have not specified what is the class, but what I mean by this is, if you have a class of problems, then you can define the max over this class. Right? Oh, okay, sorry. Yeah, so if you don't have this restriction, well then, I mean, what I mean then by problem in this case is, for example, all probability distributions, say. So. Yes, yeah, it's okay. You always have a class, for sure. But the class would be less restricted, let's say. I mean, for example, in the online case, you would have the maximum over all sequences of data points, of all pairs, all sequences of pairs. Okay. Maybe I'll skip that. So if we go the other, instead of the minimax approach, we go the competitive approach. Here the difference, and okay, here is where the difference occurs, is that instead of imposing restriction on your class of problems, what you impose is that you don't want to compare your performance to kind of the best possible performance, but the best possible performance in a certain class of predictors. So you're looking at your loss, the loss of your algorithm on the problem, and you compare it to the loss of some reference algorithm on the problem. And the reference algorithm, you take the best within a certain class. So here, I mean, again, it's not, I should have said reference is some element of a small class of algorithms, and problem is some probability distribution, for example, among a large class, possibly all probability distributions or all sequences of data or something. So you put a lot less restrictions on the problems, but now you introduce restriction on what you are comparing your algorithm to. So in a way, you're trying to do as good as some algorithm within a class for all possible problems. So this way, you no longer have assumption, and you no longer have to kind of make sure that your problem satisfies the restrictions that you put before. I mean, you don't have restrictions anymore. And okay, so once we are, I mean, studying these quantities means proving what we call upper bounds or lower bounds on these numbers. So we want to, an upper bound would be something saying that, I mean, a statement saying that this is less than some quantity, and the lower bound would be something saying that this is larger than some quantity. And to prove an upper bound, it's the only thing that we have to do is to show an algorithm, I mean, come up with an algorithm for which we can prove that the error is not larger than some value. And to prove a lower bound, we have to prove that for any possible algorithm, because we have mean here, for any possible algorithm, there is some distribution for which the error is large enough. And okay, finally, I'll get to some notation, which is kind of simple here. I will consider this pairwise prediction. So we have an input space X, an output space that we can consider as binary, so we can restrict to binary classification for now. N will be the sample size number of examples that we observe. So I'm not in the online setting here. I'm more in the offline. So I observe pairs X, Y. So I'm considering, again, the supervised learning framework. So I don't assume that I have unlabeled data. We have a loss function, which often is whether the two labels are the same or not. So that's the misclassification error. And we look at either the cumulative loss for a given function, so the number of times it makes a mistake at predicting y from x, or the expected loss, which is the expectation of this value under some distribution, some unknown distribution. That's the IID setting. We will consider, we will call dn the function that we construct after observing n pairs. And G star will be the optimal function in the sense that it minimizes the loss, the expected loss here. Okay, and the problems that we, I mean, kind of quantities that we can be interested in are like this minimax loss. So we compare the loss of a given algorithm to the loss of the best in the class. So for probabilities belonging to some class P of probabilities, or the regret approach where we compare to a reference belonging to some class G of functions, and we take the max over all probabilities distribution. So these are slightly more formalized goals. And maybe I'll stop here, and we can start again in, well, let's say in 10 minutes.